In this session, we are going to see about Pauli spin matrices. So, sigma x, sigma y, and sigma z are called as Pauli spin matrices. Pauli spin matrices are 2 into 2 matrices. So, the matrix may be either real or complex. So, here you can see sigma x is 0, 1, 1, 0, and sigma y is equal to 0 minus I 0. Sigma z is equal to 1, 0, 0 minus 1. And we can also prove that sigma squared is equal to sigma x squared plus sigma y squared plus sigma z squared is equal to 3. So, sigma x squared is equal to 1. Sigma y squared is equal to 1. Sigma z squared is equal to 1. So, when you add these three, so the solution is 3, and the summation of these three matrices, square of the summation of these three matrices is equal to sigma squared. So, we will also prove this in the coming session. The commutation relation between the two operators, sigma x, sigma y, these are called as Pauli operators. We'll see the commutation relation between these two operators. So, as usual, we have to expand this as sigma x, sigma y minus sigma y, sigma x. Substituting for sigma x, that is 0, 1, 1, 0, sigma y 0 minus I 0, minus sigma y, once again substitute 0 minus I 0, sigma x is 0, 1, 1, 0. Okay. So, you know about matrix multiplication. So, row into column. So, 0 into 0, and then add this 1 into I. Okay. So the summation is I. Okay. Similarly, row into column. So, 0 into minus I, 1 into 0. So, when you add these two, that becomes 0. And row into column. So, 1 into 0, 0 into I. So, both become 0 when you add these two zeros. So, the resultant should be written here. And similarly, this one. That is 1, 0 minus I 0. 1 into minus I, 0 into 0. So, when you add these two, in this element, you will get minus I. Similarly, here also you see row into column. 0 into 0 minus I into 1, that is minus I, that should be written here. And similarly, row into column, 0 into 1, 0 minus I into 0, that is also 0. So, when you add these two, put the solution here in this position, that is 0. So, here row into column, once again row into column. So, I into 0 plus 0 into 1. So, both become 0. So, the solution that also becomes 0. And similarly, row into column, 0 into 0. I already told that. So, this one, this row into this column, I into 1 plus 0 into 0. So, I, when you add these two, so I comes put at this position. Okay. So, now what you have to do is matrix subtraction. Subtract these two matrices. So, I minus of minus becomes plus. So, I plus I, 2I. Here 0 minus 0 is 0. 0 minus 0. So, in this position 0 comes. Minus I. So, becomes minus 2I. When you add minus I along with minus I, that becomes minus 2I. So, take this 2I as a common factor outside. When you take 2I as a common factor outside, inside the matrix, 1, 0, 0 minus 1 comes. So, that 1, 0, 0 minus 1 is nothing but that is sigma z. So, 2I sigma z is the solution for the commutation relation between the spin operator sigma x, sigma y. These operators are called as Pauli spin matrices, or we can also call these as Pauli operators. We will see the next commutation relation, that is between sigma y and sigma z. So, sigma y, sigma z can be written as sigma y, sigma z minus sigma z, sigma y. And substituting for sigma y, 0 minus I 0, sigma z in matrix form, 1, 0, 0 minus 1 minus sigma z. So, minus 1, 0, 0 minus 1, and then 0 minus I 0, that is for sigma y. And now, first do the matrix multiplication, and then we will subtract these two solutions. Okay, the solution that is obtained by matrix multiplication. So, as before, row into column. So, 0 into 1, that is 0. minus I into 0, that is also 0. So when you add these two zeros, so you get the solution as 0. Put it in this position. Okay, and coming to the second one, how to write the second element. So row into column. So this is over. Row into column, 0 into 0, minus I into minus 1, that is plus I. So the solution is plus I. Put it in this place. And then once again row into column, I into 1, 0 into 0. When you add these two, so the solution is I. Put it at this place of matrix. And now the last one, I into 0 as well as 0 into minus 1. So both zeros when you add together, that also gives 0. So the final solution of the multiplication of these two matrices are 0i, I0. Similarly, multiply these two matrices as I said before. So what you have to do is row into column. So 1 into 0, then plus 0 into I, that is also 0. So summation should be the solution should be substituted at this place. Okay, has to be written in this place. And similarly, row into column, 1 into minus I, 0 into 0. So minus I should be at this position. 0 minus 1 into 0 into I, row into column, 0 into 0 minus I. So that has to be written here. Similarly, 0 into minus 1 into 0. So both become 0. So the solution is 0, which has to be put at this point of matrix. And now what you have to do is subtract these two matrix. When you subtract these two, 0 minus 0 is 0. I minus of minus I becomes 2i. And similarly, I minus of minus I, that also gives 2i. 0 minus 0 is 0. So you'll get the answer for these matrix subtraction is 0, 2i, 2i, 0. So take 2i as a common factor outside, 2i. So within the matrix, the elements are 1, 0, 0, 1. So what is this 1, 0, 0, 1? Already you know, nothing but it is sigma x operator. So 2i sigma x is the solution for the commutation relation of sigma y along with sigma z. So here also you can see the cyclic manner of cyclic permutation you are seeing. That is after y, z comes. So in the solution you are getting this x. Okay, it should be in a cyclic way. If it is found to be in the reverse way, automatically negative sign arises. Okay. So finally we have found out the solution for the commutation relation between sigma y and sigma z as 2i sigma x.